Phew. Whee!
Boing, boing.
Whee!
Uh-oh. I thought I'd start with a general explanation of how this steam engine works. The first thing I did was I lubricated all the moving parts of the steam engine to reduce friction. And I made quite a fuss of preparing the fuel. I'm soaking a cotton wool ball with methylated spirits, which is essentially a hydrocarbon. And then I filled the boiler with water. Check the safety valve because obviously if you're going to boil water, we're going to end up with steam which can build up a lot of pressure. I don't really want that boiler blowing up. So there's a safety valve which is designed to open when the pressure exceeds a certain value, and it will release that pressure. And then I can light the fuel, that generates heat. Okay, until we've got steam. Steam goes up through that pipe. If I turn that around, you'll see that the pipe leads to a cylinder, and that cylinder contains a piston that can be pushed out by the steam, and it turns the crankshaft with a flywheel attached. I'm turning that with my finger so you can see the mechanism. The piston is connected to a flywheel, which translates the piston's movement to rotational movement of the flywheel, which in theory can then go on to turn other mechanisms and do some useful work. This is just a static engine, so the flywheel just spins and it doesn't actually do anything useful apart from the fact that it's quite good fun. Okay, let's see if we can explain how a steam engine works using the particle model. Quick title. If I draw the boiler, and I'll add the funnel, just to make it look more like a steam engine. Now, there was liquid water within that boiler, and we applied heat. The easiest way to represent that is with an arrow and the word heat. Of course, that heat came from an exothermic reaction called combustion of a fuel. Okay, so there's our boiler. The liquid water was boiled. It was transferred to a small cylinder that contained a slider that was connected to a flywheel. Okay, the gas particles, the particles of steam, push on that slider, and that slider is connected to a flywheel. It makes this flywheel turn. Okay, in terms of the particle model, we start off with liquid water, so we can represent the particles of water with a circle. I'll try and draw them all the same size because that way they represent the same substance. Each particle is the same substance, each particle is water. Now in a liquid, the particles should be in contact with another. They're quite closely packed, but they'd be randomly arranged. Okay, I'm not doing a very good job of keeping these particles the same size. The idea here is I'm trying to communicate the fact that they are randomly arranged and they are filling the shape of the container. That's my liquid. When we heat that, those particles eventually gain enough energy to overcome the intermolecular forces that are holding them together, and those particles are now free of one another. They can move with random speed and direction. There's a lot more of a gap between each particle. I'm only going to draw 3 because to fit all of those particles in I'd need a much larger volume. Okay, the gas will take up a much larger volume. I can represent the motion of those particles with arrows if I like, and I can even show how they might collide with the side of a container.
and as they collide with the side of the container, there's a transfer of momentum. It applies a force, and we end up with a pressure that we use to drive this mechanism. It's important to remember that between these particles there is nothing. Okay, a common mistake is to suggest that between these particles would be air. No, there's nothing between these particles. Each one of these particles represents a particle of water. There's nothing between them. Okay, it's important to remember also that this is a change of state. It is a reversible process. We've got a physical change. We have not got a new substance. Okay, we've got particles of water as a liquid. We've still got particles of water, but now they are a gas. It is a physical change. It is reversible. We have not created a new substance, so it is not a chemical change. If these particles lost their energy, they would become a liquid again. Now, going over to our mechanism, because particles of a gas take up a lot more volume, the only way they can really achieve that in this system is by pushing on this slider to generate a larger volume, and that forces that mechanism to work. We can, in theory, connect that to another pulley. Maybe that could be connected to a wheel, and maybe that could drive a whole steam engine along a track, for example. So we can transfer energy from this system to go and do some useful work. Okay, but the basic understanding of how it works is really down to how a liquid becomes a gas if we increase the energy of those particles, and that gas requires a much greater volume. We can, if we like, if we know what we're dealing with, we can try and quantify this process in terms of energy transferred, because don't forget we're applying heat. That is a transfer of energy. Okay, we are transferring energy to these particles. Okay, so the energy transferred equals the mass times a thing called the specific latent heat of vaporization. In this case, we're talking about vaporization. Sometimes we call gas a vapor. Okay, if we're talking about the change of state between a liquid and a solid, we'd be talking about the latent heat of fusion. Okay, but here we're talking about the latent heat of vaporization. So we've got energy, that would be in joules. We've got mass, the amount of substance, that would be in kilograms, and this capital L is the specific latent heat of vaporization. Okay, now water, the specific latent heat of vaporization of water, pure water, equals 2260 kilojoules. That's 1,000 joules per kilogram. What that means is we would need to transfer 2,260,000 joules of energy to 1 kilogram of water for it to change state between a liquid and a gas.